We've been talking about refining metals, getting them into a form that we can recognize as metals, and we've been talking about putting them together and making alloys, but none of this is of much use to us unless we can get this metallic material into a usable form. There are two basic ways to get the material into a usable form, and they are cold working or hot working the material. Of course, we can shape it by other means, and that is to say we could machine it as well. Before I start talking about this, I would like to set the record straight on something that I told you of necessity in the first lecture. When I said that all solid metallic materials are crystalline, I knew full well when I said that that wasn't so, but it enabled me to talk about the materials because most all solid metallic materials are crystalline. And up until 1960, everyone in the field thought that that was true. In 1960, Dr. Paul Douay at Caltech found out that if he cooled a metal, an alloy, that was in a liquid state sufficiently rapidly, then he could cause the material to retain this state that it was in. And the state it was in was a liquid, except the material could take a shear stress or was a solid. So what he was able to do was to make the material which was amorphous, non-crystalline liquid, all of a sudden turn out to be an amorphous solid material or non-crystalline solid metallic material. He did this by taking a tiny little droplet of material and getting it molten, this small particle of material, shooting it from a gun at a copper toboggan. And this copper toboggan was very, very cold, and the metal smeared it on this little toboggan, and he wound up with a little chip of metal, a metallic material, which when he x-rayed it turned out to be a glass or an amorphous material. And so in 1960 we moved into an era of looking at metallic glasses. And since this is one of the more exciting things in the field today, I wanted to tell you about this, and in a few moments I'll show you what the current process is for making the material. Actually, if we wanted to make all of these little tiny chips of amorphous material, we could, by powder metallurgical techniques, effectively bond them together, or we hope we can. But it would be nice to be able to produce them en masse, a lot of material, tonnage type material or poundage type material. And such processes have been developed, and we want to look at one of those processes this morning. Well, you will recall in the process of making steel or even non-ferrous materials, we talked about continuous casting, and this is the model that we considered. That is, in a horizontal caster, we have one situation. In a vertical caster, we have another situation. In this particular case, we're going to cast horizontally, and the cooling die, the water-cooled die, is this particular die. And the molten metal is fed into a holding pot, a tun dish ahead of it, and as long as we cause the molten material to flow into this cavity, we can solidify it. Now, there's going to be a liquid-solid interface that appears here, and actually you can see this better in the next slide because in the next slide we see that we have a vertical caster, and the molten material is being fed from the top, comes down through a little channel. It goes into the water-cooled die on both sides, and it could be almost any shape you want, a cylindrical section or say a square section or a rectilinear section, but we are extracting the heat from the molten metal, and it becomes solid. And if we look at the solid, which is the pure white material here, you find that it travels up along the side, or the molten material is being solidified just in this zone. That's the liquid-solid interface. And as we continue to pull this from the bottom, we spray water on it to make sure that solidification is completed, and we get the solid metal out of the bottom. So this is called continuous casting, and this particular continuous casting process is the one that we use today to save a lot of money in the steel industry and get better products. That means products with fewer defects. Well, in order to show you a continuous casting, I'm going to show you the world's smallest continuous casting, actually, because we're going to make a ribbon by a process that's currently used today to make amorphous metals. Now, we're only going to do this with tin. And the reason we're going to do it with tin and not try to make an amorphous metal is because most of the amorphous metals are produced at high temperatures because they are of alloys that have high temperature melting points. And you wouldn't want to do it in a classroom setting. But the technique that's used today is successful in producing sheets that are as wide as 4 inches, 5 inches, or little tiny ribbons, or powders, flake powders, or almost anything. Well, I've asked for a volunteer to help me this morning, and what we're going to do now is we're going to melt some tin, a little bar of tin, in a tube, in a glass tube, that has at this end a tiny orifice. Well, the orifice is fairly large. In this one, it's about 20 thousandths of an inch in diameter. But we'll put the bar of tin in this glass tube, and then we're going to be interested in melting it. And what's going to happen is it's going to pass from this glass tube onto a cake pan. This is a very simplistic piece of apparatus, but it's just a 9-inch cake pan, an aluminum cake pan, that will be rotating. When we squirt the molten metal on the surface, it will stick to the surface on a wheel for approximately a ½ inch. And during that period of time, it will solidify. Actually, during that period of time, the quench rate on the material will be about 1,000,000 degrees per second. And we have measured this. We know this is true. It's that rapid quench rate from the molten material to the solid material, which, if you have the right alloy, will turn it into an amorphous metal or a metal glass. So, in essence, there have to be 3 different parts to the process. You have to have a heater that we can melt the material with. And you have to have something to eject the metal with. So we just used a little squeeze bulb to push it out. I could blow it out with my mouth if I wanted to, but this is a little safer. And so I'll be melting the molten metal and taking it over this wheel. And let's move it, let's say, just about to this position, if you will. And actually, it cools so fast, I could get another volunteer up here, because it's going to be 450 degrees on this side when it hits the wheel, and I could get you to come over and you could catch it in your mouth on the other side. But he doesn't want to do that. All right, so we won't do it that way. Well, it takes a few moments to melt this, and I just want to tell you that this demonstration's been a lot of fun for me, because I generally ask permission to do this if I'm in a hotel or even a TV studio, and they say, sure, go ahead, that's all right, no problem. But they don't appreciate that what I'm doing is disintegrating the metal. And the disintegration process means I'm going to break this metal up into lots and lots and lots of surface area and footage, and so I'm going to mess the floor up. And I generally get in trouble in hotels, but I hope I won't get in trouble here today. Well, the metal is melting. It's almost molten. But gee whiz. We have to plug that drill in, I'm sorry. Would you do that, please? Okay, are you all positioned right now? Now if you focus on this, on the wheel, and you watch what's going to happen. Turn it on. Okay. Now if you'll gather up that stuff for me and bring it over here. This is continuous casting. Certainly we went from molten metal. Just gather up a big handful, scoop it up with your hand, And that's right, and just hand it to me. Great. And you see, the process produced, thank you very much, the process produced for us little tiny ribbons. If you get this in your hands a little later on, they're pretty tiny. It's hard to inspect them, to focus on it here. But if you get them in your hands and look at it, you find, hey, the stuff talks to you, you know. You don't have any problem knowing which side of this was the cake pan side, because it's going to copy the image that's on the cake pan. If I wrote my name wrong side outwards, you know, backwards or wrong side out on a cake pan, if I engraved it in there, we could have my name engraved on each little piece, you know, over and over and over and over and over. And if you look at the other side, it looks sort of bumpy, sort of broken up, and actually they are called Smolowski cells, or they are the little elements, the branches of the dendrite. So there are a lot of little dendrites that are growing up from the bottom, and you can see all of that. Well, now if you can imagine this being done to produce a sheet that's, say, 4 inches wide, 6 inches wide, and you say, hey, that's a pretty good method of making sheet stock. Even if it were in amorphous, it might be pretty good. In fact, if we could make it about 12 inches wide and do it in aluminum, it'd be a great way to make rigid can stock for making beer cans. So there are lots of people interested in this today, and I thought I would be amiss if I didn't tell you about that. But does it have a practical use? The answer is, it really does. One of the uses is, if we make this material out of an iron with 20% boron in it, we find that this material becomes very magnetically soft. It's ideal for a transformer. The power loss in a transformer would be much less if we could make it out of this particular material, this iron boron material. Except that we need to make wide sheets. And so companies like Allied Chemical today make and sell wide sheets of this material. GE and Westinghouse make it into transformers, and these particular transformers are more efficient transformers. And if we learn how to do it real well and bring the cost of the material down low enough, then we would have it as motor sectors and in drills and in lots of places. It'll have a lot of use. What's another advantage of it is that it doesn't have any grain boundaries. It's amorphous. It's just a continuous material. And so when we do corrosion in one of the later lectures, you'll find out that grain boundaries are a source of a lot of problems. And if we don't have any grain boundaries, we expect to have a material that's going to be more corrosion resistant and becomes pretty exciting material to have around. Well, we have lots of other methods of doing hot working of the material to make a product. And what I'd like to do is I'd like to run through a series of these, and when I'm all through, I'd like to go back with you into a steel mill and follow by recitation what's happening in the hot working process to produce a product, an end product that you all know and are so familiar with and sometimes doesn't talk to you, but I want it to talk to you. So let's start by